Welcome to Spring LIB.
So a proton is traveling with speed 8.65 times 10 to the 7 rather, meters per second. Okay. So if you divide that by the speed of light, you get 0.2883, speed of light being 3 times 10 to the 8 meters per second. So this means that velocity in terms of speed of light is 0.2883 times the speed of light. And the advantage of writing velocity this way is that we can work out what gamma is, which is 1 over square root of 1 minus v squared over c squared. And so that's just 1 over 1 minus this thing squared, 0.2883 squared. That gives you 1.0443 for gamma. Okay. And so now we use the relativistic equation for kinetic energy, which is Ke equals gamma minus 1 times rest mass energy squared, rest mass energy, so that's mc squared. This is 938 MeV from the book. And of course, gamma minus 1 would be 1.0443 minus 1, so that's 0.0443. You multiply them together, and you get 41.6 MeV. Also, we find momentum with equation 26-4 from the book, which says the momentum is gamma times mv. And so you have a gamma times, which is that, times m, which is 938 MeV per c squared, because remember, energy equals mc squared. And once you have a value in MeV, you can just divide that by c squared to get the mass. And this times velocity, also in terms of c, it's 0.2883 times c. One of the c's cancel. And what you get is about 282.4 MeV per c. So these are your relativistic kinetic energy and relativistic momentum. Now we look at the classical case. So classically, kinetic energy is the familiar 1/2 mv squared. Here's where we'll use the mass of a proton that's given to us, 1.67 times 10 to the negative 27 kilograms, times the velocity that's given to us, which is 8.65 times 10 to the 7 meters per second squared. And so this gives us something very close to 39.0 MeV. Already, as you can see, that's a different value from that, the relativistic case. Momentum is just mass times velocity. Okay, and so mass is this, velocity is that. All that's different here is a factor of 1/2, and the v is not squared. And so you get 271 MeV per c when you plug those numbers in, which, as you can see again, is different from the momentum here. So the error the percentage error will actually be the difference over original, right? And you'll have to multiply that by 100 to get the percent value. Okay. And so let's work this out for KE. Let's use a different color. For KE, percent error equals the classical the relativistic minus the classical over the original, which would be the relativistic times 100%, right? And that gives you, pardon me, it will be divided by the 41.6, which was the actual relativistic KE. And so that gives you negative 6.3% when you work that out. Okay? And finally, for momentum, the percentage error is 271, which is the classical value, minus 282.4, which is the relativistic true value, over 282.4. Multiply that by 100%. What you get out is negative 4.2%. So the moral here is that kinetic energy and momentum both change, both vary by a significant percentage when we use our classical approximations for this very fast-moving particle. So another merit of using special relativistic calculations is that this error goes away. So there you have it.